This is question on standing waves and harmonic and oscillations. So for this question, we have wave generator, the green box. So you have the wave generator here, and it vibrates at certain frequency, and the wave is being sent. If on the other side this part is not fixed, the handle right there is not fixed and free to move, then when the wave is reflected from the stand on the other side, on the right side, the wave is going to follow the same direction. However, if the handle right here is fixed and cannot move, then when the wave is reflected, it will be reflected in 180 degrees with a 180 degree shift. So it's gonna go like this. And when such wave is reflected, a standing wave occurs. So if on the other hand, at certain frequencies, standing wave will occur. Not for every single frequency you will reach the standing wave. So for but you can reach standing wave this way. So when the wave is reflected, there are different ways to look at the reflection of the wave. So if it goes from the denser medium to the thinner medium or less thick medium, if the wave is going this way, it will continue going through the thinner medium, probably with a bigger amplitude. Let me redraw this. So if you go from thicker medium to thinner medium, and the wave was going this way, partially the wave is going to be reflected. So when it reflects from the thinner medium back to the thicker medium, it's going to be reflected in the same phase, maybe with less amplitude, because some of the waves will continue going, or in this case it will continue going this way, the way it was going. But if you were having less dense medium going into the denser medium, maybe air and water, the wave that would enter the denser medium would reflect back with the phase shift, and then the rest of it is going to continue going, but not at the same amplitude, because partially the wave is lost, and then also there's more molecules here to erase and put down for oscillate. So the wave is not going to have the same amplitude as it used to have. So this is when you have denser and denser mediums. But then if you have fixed and not fixed attachment on the other side, let's say for this type of wave, and this is transverse waves. So if you watch the videos in the other video that I posted about the waves, they're transverse and longitudinal waves. So this one is a transverse wave because every single particle, so the wave moves in this direction, but every single particle in the wave moves perpendicular to the motion of the wave. So if this wave is created and is attached right here and cannot move, the wave is going to be reflected with a 180 degrees shift. But if the wave is not attached, or the string is not attached and is free to move, so it gets there and can move up and down, then it will be reflected with the same phase shift. Okay, so this is important to know because there are different ways to look at these problems that we're going to be looking at. So first, let's look at, and it's called standing wave. When you get the wave that is looking like this, it looks like a standing wave because you have both waves that is coming and going back, or reflected, and it looks like a standing wave. And again, there will be more videos where you can see the videos that I showed posted for you, and you will be able to see the behavior of the wave and the standing wave as a demonstration. So for this part, let's say that the length of the, actually let's look it up here. Let's say we have the length L of the rope, and I'm going to make it smaller so I can fit both examples. So I have length L of the rope. I could send the wave, let's do it this way. I can send the wave and it could be reflected this way. Or if I had higher frequency, I could send the wave at higher frequency and it would be reflected this way if I'm talking about the fixed side on the other side. Or I could also do another one and maybe a wave at this frequency, then the wave is going to be reflected to cause the standing wave like this. Or let's do one more, or maybe another wave, and the wave is going to be reflected. Another wave, let's do, and the wave is going to be reflected this way. So for I'm going to have another part of my whiteboard on the other side. So for this case, if the length of the rope is L, if you watch the videos about the wave has certain characteristics. So one wavelength is the point from where it starts to the point where it goes back to the same position. So you see right here, it rises to the point where it rises. This is one wavelength. And the wavelength has measured in meters. Like if you had the ruler and you had to measure the wave, you would use lambda, and that is measured in meters. That's the wavelength. You could also say the wavelength is maybe from the crest to the crest. So this is the crest, this is the crest. You could say, okay, this is the wavelength because it's the same point on the top of the wave, the wave when the wave repeats itself. You could also use, let me make another wave. So equilibrium point, and I have the wave, and I want to see what's the wavelength. I could also say it's this point and this point, as long as they are the same point of the wave. Or maybe it can be this point and this point when it goes up and up. Or maybe it can be this point when it goes down to the next point when it goes down. I can say this is the wavelength. So that is the wavelength. There's also an amplitude. How far from the equilibrium will the wave be displaced? And another thing is the time. So this one amplitude, which is A, and another one is the time or period. How long will it take to go from the crest to the crest? Or how long will it take from the time it goes up to the next time it goes up? Or how long will it take from the time it goes down to the next time it's going down? Or maybe how long will it take from this point to this point? So in other words, how long does it take to travel one wavelength? So that one is called the time, is called period, and measured in seconds. So when the wave completes one full motion around itself, like the revolution, it is called the period. Time takes to do one revolution. So that is the wavelength. So if I look at my problem that I drew on the left side, my what I see here in the first top graph on the left, I don't see the full wavelength. I'm missing this part for the full wavelength. So what I see is my L is actually equal to 1/2 of the wavelength of the wave. I can also look at the second one and say, oh, if this is the length of the rope, then in this case my L is equal to the wavelength. And if I look at the third graph, then I fit one full wavelength and a half. So I have L is equal to 3/2 wavelengths. And if I look at the last one, its L is equal to 2 wavelengths, because you have one wavelength and 2 wavelengths fit in this graph. So I want to also show you something interesting here. Instead of writing lambda, in this case, I'm going to write 2 over 2 lambda. And instead of writing 2 over here, I'm going to write 4 over 2 lambda. So what's interesting in here is this. I can continue making my examples, but I see a pattern. If both sides of the waves are fixed, here is when it's produced the wave, and here is when it's reflected. When both sides of my wavelength, my wave fixed, L has the relationship n over 2 lambda, because my n is 1, and then it's 2, and then it's 3, and then it's 4, and I can continue. It's going to be 5 and 6 and 7. So my n is equal to 1 and 2 and 3 and 4 and so on. And this 1, 2, 3, and 4 are called harmonics. So this one is called first harmonic and fundamental. This one is called second harmonic. This one is third harmonic, and so on. Also, the first harmonic has 1 node and 2 antinodes. Has 2 nodes. These ones are called nodes. This one has 2 nodes and 1 antinode. And the second harmonic has 3 nodes. This one's called nodes, and 1, 2 antinodes. And the third harmonic has 1, 2, 3, 4 nodes and 1, 2, 3 antinodes. And the fourth harmonic has 1, 2, 3, 4, 5 nodes and 1, 2, 3, 4 antinodes. This is just interesting to keep in mind when you're looking. Sometimes they ask you to find nodes and antinodes. So important parts here to remember. First harmonic, second harmonic, third harmonic, fourth harmonic, and it's harmonic, the word harmonic. Then first harmonic has 1 antinode, second harmonic has 2 antinodes, third harmonic has 3 antinodes, and so on. I'm gonna clean a little bit here and then rewrite something else. Let me clean and I'll be right back with you. So I cleaned this a little bit because I needed for a little bit more explanation here. Again, from the wave lesson. So there were amplitude, frequency, period, and there is a velocity of the wave. The velocity of the wave, velocity is measured meters per second, so it is wavelength over the time it takes to make one period. Or you could rewrite, again from the lessons about the waves, there is such thing as frequency, and frequency is how many waves occurs within 1 second. So how many times you will see a wave within 1 second, or how many waves pass a point in 1 second, is called frequency. And the frequency is measured in hertz and equals to 1 over the period. And it is measured in hertz. And hertz means 1 over second, how many times a second. So here I see I have 1 over t. So the other way to write this formula is also lambda frequency. So the velocity of the wave can be found using the formula v is equal to lambda over period, or lambda times the frequency. So this would be for velocity of the wave. Now, frequency only depends on the source. Frequency does not depend on anything. So you can have, I'm going to talk about the wavelength, or about the light wave. So let's say I have an ocean, and here you have air, which is just particles of air, not very dense. And then you have water, which is much denser. So when the wave is coming, when the light wave is coming into the water, there's more particles to interact with in the water, so it slows down, And when it slows down, it changes the angle at which it passes through the water. And then let's say if there was no more water after this, and it was just the air, then when it comes out, it still has the same angle as it used to have when it came. So this one is called the incident ray of the wave, or the light, and this one is refracted, and this is just the one that is passing. So the velocity will depend on what medium the object is traveling through, and so the frequency only depends on the source. So in this case, it would be the sun. It produces this frequency light, and there's nothing I can do about the frequency. So if I look at certain spectrum in electromagnetic waves, like radio waves, visible light, ultraviolet, X-rays, gamma rays, all of them travel with the same speed in the vacuum, but when they enter a different medium, they slow down. And every single wave, like gamma rays, have the highest frequency and the highest energy of all the electromagnetic waves. So what I want to say is this: the velocity is equal to the wavelength times the frequency. If the frequency of an object only depends on the source, so just because it entered water, the frequency of the object does not change. It's still going to pass so many waves in 1 second. But what does change is velocity in the wavelength, because the frequency is equal to the velocity over the wavelength. So if your frequency stays the same and the wavelength and the velocity went down, so had to do the wavelength, it became shorter. So it became smaller, right? It became so coming back to our problem here, the examples, I can write the wavelength for the first harmonic or fundamental harmonic is equal to 2 times the length of the rope. In this case, it's the same, so I can write it this way, and I can write it this way. In this case, I can say lambda is equal to 2 wavelengths, 2 times the length of the rope over 3. And in this case, let me erase that part so it's not confusing. And in this case, I can say that my lambda is equal to 1/2 of the length of the rope. But all of them had the same generic formula. L is equal to n over 2 lambda, where n was equal to 1, 2, 3, 4, and so on. So this is the same for every single wave that has both sides fixed. I'm going to look at another example that has both sides not fixed, like maybe sound wave. So if I have both sides not fixed, I'm going to make a pipe. So I'm going to have this pipe, this pipe, this pipe, and it's open on both sides. So in these pipes, they're open on both sides. So if the wave enters into the pipe, the first harmonic is going to be like this. The second harmonic is going to be like this. Oh, and reflects this way, because when you blow air into the pipe, again, watch the video so you understand how that works and how it changes the frequency, because just my explanation alone is very difficult to understand. The videos are important with the explanations, and I'm going to post a few of them into my links for this video. So the first, when you blow, there's going to be less molecules inside of the pipe than there are outside of the pipe. So it looks like it's more dense air outside than it is inside. So when the reflection happens, it is 180 degrees shifted. So in this case, I have again shifted, and then for the next harmonic, I'm gonna have this much. So looks like, oh, did I do it extra? I think I did extra here. So for this one, I needed to do it. So here was one full wave, right? This is full wavelength. It goes from the top to the top. So for next one, I have to do 3. So that would be, let me fit 3 here. Right. So one full length and a half. And then the last one, I have to fit 2 of them. So 1 and 2. So when it reflects, it looks like this. So messed up here again. So this would be the wavelength, this would be the reflection. And if you look on the graph, it's still the same formula for this one, for this one, for this one, and for this one, because you go from here to here. That's not the full wavelength. You need another half of it to make the full wavelength. So you only have 1/2 of the full length, the same as when you had both sides fixed. This one 2 open. Here you had 2 sides fixed. You had the reflection this way. Here you have again, you have full wavelength from the top to the top is going to be, from the crest to the crest is going to be full wavelength. So the formulas matching whenever you have both sides fixed or both sides open or free to move. But they do change. So for, I would say, I'm going to come back to this. Let me show you another example, and then I'm going to come back to this example. Here, I'm going to free a little bit of space for myself. I'm going to show you another example here. I still have a rope, but now my rope is not fixed on the other side. So my wave would be free to move from here to that, and then it would reflect this way. Then if I have the next harmonic, again, it's fixed on this side but not fixed on the other side. I could have something like this, but it would reflect back this way. And for the next harmonic, again, if it's fixed on one side but not fixed on the other side, like with the rope example, with the rope like we had right here. So if it's not fixed, it's free to move there and back by the time the wave reaches the rope. So for the last one, I could have the next harmonic that maybe looks like this, and when it's reflected, it looks like this. So when I look over here, I'm actually missing this part of the wave and this part of the wave. So if I continued, I'm missing 1 part, 2 parts, 3 parts of the wave. So what I see only 1/4 of the wave, because in order for the wave to be a full wavelength, it needs to go from here to here, and I only see 1/4 of it. So here I'm gonna say if this part is L, then your L is only equal to 1/4 of the wavelength. Then for the next question, what I see is I'm missing this part. So I have 1/4, 1/4, 2/4, I have 3/4, but I'm missing the 4/4. So what I see in this case is L is equal to 3/4 of the wavelength. And then for the last one, let's see how many quarters I have. 1/4, 2/4, 3 quarters, 4 quarters, I have 5 quarters. So I have 5 quarters of the wavelength. And it would be the same with the pipe. So let's say if the pipe was only open on one side but not open on the other side. So if I have it open on one side and not on the other, when the wave comes in, I would have this, and I would have reflected wave. I would have this, and I would have reflected wave. Or I could have this, and I would have reflected wave. So again, on both sides fixed, I have 1/2. Let me show what I'm talking about because you may not follow me. I have 1/2, I have 2 halves, I have 3 halves, I have 4 halves. For one side closed or fixed, I have 1/4, I have 3 quarters, I have 5 quarters. So I can kind of see my generic formula over here. I can say the generic formula. So for the previous question, generic formula was that L is equal to n/2 lambda. So I could use this formula for every single problem that is fixed or open on both sides. But for this one, I see my L is equal to n, and it's good to know that n is equal to 1, 2, 3, and so on. In this case, n/4 lambda. But n in this case is equal to 1, 3, 5. So generic formula for one side closed, one side open, not same, odd ones. Has odd numbers for n. So if you have an odd situation when one side is open, one side is closed, I say it only has odd numbers for n, and it's over quarters. And if you have an even situation where both sides open, both sides closed, you have an even situation where you have n is equal to 1, 2, 3, 4. So this is good to know for standing wave, and it's used a lot for oscillations. And here is more example of what it would look like if without my drawing. So you see antinodes, and you see the nodes, they mark them as nodes, and again nodes and the antinodes. Also, what's interesting is, so this is both sides fixed or both sides open, and this is one side fixed and one side not. And here they call it fundamental or first harmonic, second harmonic, third harmonic, fourth and fifth, and so on. But in this case, they say fundamental or first harmonic, and then because it's the third harmonic, because it's 3 over, so it's 1/4, right? It was 1/4 L is equal to 1/4 wavelength. Here you had 3/4 wavelength. Here you had 5/4 wavelength. So they call it first harmonic 1, third harmonic 3/4, fifth harmonic 5/4, seventh harmonic 7/4, and so on. So that is good to know. And the video is already 30 minutes, so I want to cut it off here, and I'm going to show you a few examples of how to use what you just learned over here.